Excellent.
Great.
Yeah, I can see it.
Okay, great. So anytime you're ready.
Fantastic. So welcome, everybody. It's a great pleasure to have Mukund Rangamani all the way from the west coast of the US. It's very early for him there, so I really appreciate taking the time to speak to us about his recent paper on 3D disordered superconformal fixed point. Mukund, this floor is yours.
Thanks, Jeff. Indeed, as Jeff said, it's great. It's a pleasure to be speaking to you folks, and I'll talk to you today about something I was working on for the last couple of years with our former postdocs, Qiming Chang, who is now in Tsinghua in Beijing, Cheng Peng, who is also in Beijing at the IDP, and my student, Sean Colin Ellerin. The paper came out about a month ago, and the aim was to try to understand whether we can leverage recent understanding of disordered field theories to find new non-trivial fixed points in dimensions higher than 2. So I'll specifically talk about a model in 3 space-time dimensions. And let me give you roughly a set of motivations. So I'll have a few slides that I've written, and then later on for the second technical part of the talk, I'm just going to hand drive as we go along. So there's a sort of historical interest in trying to understand systems with disordered Hamiltonians. There's been lots of progress in long distant past trying to understand spin glass spaces in spin systems and so on. But one important fact about these models is that they offer a certain a notion of tractability that typical standard unitary quantum field theories don't. And one natural question is, given that they are tractable, can we use them to find new fixed points? And are those fixed points interesting? Are they strongly coupled? Do they teach us something new about quantum field theories? My personal interest, in part, is to do with the fact that there are very few quantum systems where we can compute and study thermal observables in real time. Let's see, the examples I know where you can do this in great detail are examples that are holographic, where the computation is simplified because you do some classical computation in the dual black hole background, but not so much directly in the context of just field theory. I mean, I'll just give you a simple example. So let's say you want to compute some natural question like take a 5 to the 4 field theory, perturbation theory in 4 dimensions, and ask, I want to compute something like a dissipative coefficient in like a viscosity in perturbation theory at finite temperature. This is a formidable calculation. This was carried out in the 90s by various people with an aim towards understanding how to do these calculations in QCD. But this is not a calculation that's easy to do, because you have to resum a lot of infrared divergences to get finite answers, partly because things like dissipative transport diverges in perturbation theory. So it's in fact, if you have no interactions, there is no dissipation. And so you see that viscous coefficients are diverge in the limit of non-interacting theories. And so if you really want to understand strongly coupled correlated systems, you want to have some insight into transport, into some thermal properties, and that's not easy to do if you don't have handle on computational handle on the fixed point. So I'm going to use disorder as a proxy in this example, and this is really what motivated us to start studying these kind of examples. And of course, there's an interesting payoff, which is, as we've learned from the study of the SYK model, there are potential connections to holography, though I'll try to spell out what exactly I mean as we go along. Much of the recent focus, and at least these ideas have been brought to fore with the much improved understanding thanks to the SYK model, which is now about 6 years or so old, and there have been many investigations, but a lot of the investigations in this context have focused on models which are quantum mechanical, i.e. in 0+1 dimensions, where there's a lot of tractability, but it sort of doesn't quite capture the full gamut of complexity of quantum field theory. There's a few investigations in 2D, primarily a very important paper that was written a few years ago by Jeff, Douglas Stanford, and Ed Witten, who looked at models in 2 space-time dimensions and found interesting phenomena there. I'll comment on some of them as we go along. But I do want to point out that 2-dimensional conformal systems, 2-dimensional critical systems, are also special because the conformal symmetry in 2 dimensions is enhanced to a full infinite dimensional Virasoro algebra that further constrains various properties. For example, as we will discuss later in the talk, thermal observables in 2-dimensional conformal systems are pretty much obtained in infinite volume from the vacuum correlators. So there's not new information in thermal observables. So it's very hard to distinguish strongly interacting fixed points in 2 dimensions from a generic 2-dimensional conformal field theory. The general characteristics are pretty much fixed by conformal symmetry. So with that in mind, let's try to ask, what can we do about constructing models in higher dimensions? What kind of challenges do we have? Is it easy to construct models? The first problem is really the problem of finding fixed points in higher dimensions. We know that in dimensions bigger than 2, and generally in dimensions bigger than 4, they don't and more generally in dimensions bigger than 4, we just don't seem to have interesting fixed points, very many interesting fixed points, certainly not without supersymmetry. And the challenge really ends up being the fact that there are no fixed points with just pure matter, no fixed points with typically just bosons and fermions without including gauge fields. The exceptions are in between 2 and 4 dimensions, where we can have Ising-like fixed points, which are critical models of the Wilson-Fisher kind. Now, so we'll try to look for something of that kind, because that's all we want to do. We don't want to study disordered field theories with gauge fields in particular in this discussion so far. And I think that's an interesting question to ask, whether including gauge fields and disorder leads to something richer than what we've explored so far. But there's a more basic problem if you just decide that you want to study a model with disorder, which is that if you have interactions which are disordered, then it's not a priori clear, and in generally just not true, that you have positive definite Hamiltonians. If you have couplings that can take either sign, you really have to worry in bosonic systems whether the vacuum is stable, because your Hamiltonian can have either sign. Pure fermions would have been fine, except that non-trivial interacting Fermi field theories don't exist in dimensions bigger than 2, for reasons to do with the fact that fermion canonical dimensions ensure that the Fermi couplings start to become irrelevant very quickly as you go up in dimension. So you need some balance. You need some balance. You need some bosons. You need some fermions, and you need something else to make sure that the Hamiltonian is positive definite. So given this, so let's try to ask, what can we do? And the obvious thing to do is to sort of constrain oneself to build a model where you mitigate the biggest problem. You ensure that you have a Hamiltonian with disorder that is non-negative definite. And the one way to do this is to use supersymmetry. So we'll use supersymmetry to guarantee us that we have a positive definite Hamiltonian and non-trivial interactions. There are examples in various dimensions, but my focus today is going to be on 3 dimensions. And I'm going to look at a model with, we can look at models with various numbers of supercharges. There was a study a few years ago by Fedor Popov, who looked at a model with 2 supercharges. I'll focus on a model with 4 supercharges for reasons I'll explain in a second. So that's a sort of broad principles of what we have in mind. We're going to look at a 3-dimensional field theory, which I'll outline for you in a second, where we're going to have 4 supercharges, n equals 2 supersymmetry, and we're going to ask, let's make the interactions disordered So we're going to draw some couplings from some random ensemble and ask, after disorder averaging, do we flow to a non-trivial superconformal field theory? And what are the characteristics, what properties of the superconformal field theory can we understand and study? For a building block, so I'll parameterize the superspace. It's a three-dimensional, I'll work in Euclidean signature. So I'll look at a superspace R3/4. So I have 4 supercharges, so 4 Grassmann coordinates and 3 standard bosonic coordinates for my superspace time. And I'll use capital variables without any indices to indicate the super coordinates. And my basic actor is going to be a chiral superfield, which has as its components a boson spin 0 field, a fermion, and an auxiliary field F. And for those of you who are not quite familiar with chiral superfield terminology, this field is annihilated by 1/2 of the super derivatives, and it satisfies a chirality condition. That's why it's called a chiral superfield. It doesn't have an expansion in terms of both thetas and theta bars. It has only thetas, and the theta bar dependence is buried through this bias in the argument. So what kind of interactions are we going to write down? Well, we're going to write down, so we can think either in terms of the superfield, which will be convenient when I talk about other stuff later, or you can think of a system where you have 2 sets of bosonic degrees of freedom, phi and f, and fermions psi with the alpha index running between 1 and 2. Okay, so think of it as a 2-component fermion and 2 bosons. The Lagrangian will have a canonical kinetic term. So this part will have d mu phi, and the Dirac kinetic term psi bar d/psi, and the auxiliary field F will not have a derivative kinetic term, it will just have an F squared. And this part, which I've written as that just comes from the Kähler term, the superpotential I have taken to be a cubic functional of my chiral superfield phis with a coupling which has index which is G. I've also allowed myself to have n chiral superfields with the I index labeling which chiral superfield I'm looking at. So this is a coupling between n different fields, some cubic polynomial built out of the phi i's, where the coefficients of this cubic polynomial are taken to be Gaussian random. Okay, but before we go and study what that does, let's just quickly see what kind of couplings we have here. That phi's are cubic. I have a half integral over half of superspace. So this gives me interactions of the form phi psi bar phi psi psi and phi squared f, which if I realize the fact that f starts out without a kinetic term, f is like a Lagrange multiplier. If I integrate out f with the fact that it's just Gaussian in the kinetic term, then this will lead to interactions of the form phi to the 4 and psi psi phi. So Yukawa couplings and phi to the 4 interactions. So the moment you integrate out f, which is auxiliary, this looks like a standard phi to the 4 theory with Yukawa couplings. So this is a supersymmetric version of the Wilson-Fisher theory. And you can either view this as a standard Wess-Zumino model in 3 dimensions with disordered couplings for n chiral superfields, or more simply as a superising model with n equals to supersymmetry with disordered couplings. And analysis a la Wilson-Fisher, which was done for supersymmetric theories as well many years ago, will tell us, naturally tells us that this theory should float a non-trivial fixed point in 4 dimensions, because phi to the 4 theories do float non-trivial fixed points in 3 space-time dimensions. And the question is, can we do more than say that there is a fixed point? Can we actually study that fixed point in some detail? thanks to the fact that we're not studying a single field theory, but rather an ensemble of field theories where the couplings are disordered. Let me pause here for a second to see if there are questions about the setup, and then tell you something more about what we can learn from this setup.
No, not for me. That was pretty clear.
So as I said, the couplings G's are random. So I'm going to take them to have 0 mean. And I'm going to take them to have a variance, which is set by some coupling constant J. But I'm going to normalize this to have to be going like 1 over n squared. This ensures that the theory that I started with will have a sensible large n limit. Okay, so I will require that I have a sensible large n limit, that this is not going to be quite like a planar large n limit or a vector large n limit. We'll see what kind of large n limit it is, but I want a systematic large n expansion for observables, and that requires me to take the variance to be scaling like 1 over n squared. What symmetries do I have in the theory? Well, if you stare at this at these chiral superfields, these fields are complex. I have a phi bar and a phi. So I can rotate the phis by a phase. This is a cubic interaction term. So I can rotate each of the phis by a phase, which is a cube root of unity. And the phase cancels against the phi bar. So there's a Z3 discrete symmetry. But it's also supersymmetric theory where the thetas have R charge 1 or minus 1. So the phis have to have R charge, and the canonical assignment in the UV of the R charge is 2/3 for the phis. So we have a U1R symmetry and a discrete Z3 symmetry and no other global symmetry in the problem. So now we can just ask what happens if we start with this theory, which started out its life as a free set of n free bosons and n free 2-component fermions with a quartic phi to the 4 and a Yukawa interaction. What happens as we flow to the infrared? Well, in the UV, we can just read off the canonical dimensions from the kinetic terms, and phis have canonical scaling dimension half, and the psis have dimensions 1. But if, as we believe, theory flows to a non-trivial fixed point, the fixed point will be one which is completely governed by the superpotential, not by the kinetic terms. And the superpotential, if we end up with a fixed point, the superpotential has to have a non-trivial R symmetry, because a fixed point, a superconformal field theory has an R current in the superconformal multiplet, which is non-anomalous. Sorry, which can have an R Toft anomaly, but there must be a non-trivial R symmetry. And you can just read off from the fact that this is a cubic interaction, that the R charge in the infrared of the phis must be 2/3. But since the R charge must be 5/3 and phis are chiral, their conformal dimension is a priori fixed by the R charge to be also 2/3. So the phi, the bosonic component of the chiral multiplet, must have R's conformal dimension 2/3 if there is a fixed point. And so even without doing any analysis, the power of supersymmetry in this example is to basically say that if there is a fixed point, there is one with a particular conformal scaling dimension for the phis. And this can indeed independently checked in this example, because as I'll show you in a second, the large n analysis means that the perturbation theory can be organized in nicely in Schwinger-Dyson terms, and the Schwinger-Dyson equations truncate because they're doing disordered averaging. So exactly like in the analysis of SYK, we can do the following. We can try to compute the quantum corrected propagator for the system by summing diagrams, and the summation beautifully truncates into just a class of melonic diagrams, and all we are left with is to resum these diagrams and check for consistency. So for example, I wrote down here, directly in line with the usual SYK analysis, the quantum propagator for the phi field, which has a part coming from which has an expression as a geometric sum. There's a piece coming from the bare propagator and the self-energy term, and the similar expressions for the fermion and the auxiliary field. You can then pick an ansatz which says that the Green's function for the bosons and the fermions have scaling properties with definite scaling dimensions, and just solve for the scaling properties by looking for the self-consistency between these equations. And indeed, you find that the phi has conformal dimension 2/3, and the normalization of the 2-point function is set by the coupling J. So this part of the analysis is pretty straightforward. And once you've got the canonical scaling dimension for phi, we can immediately write down what the scaling dimension for the other fields are. They're just given by supersymmetry. So we'll see that delta psi is 2/3 plus a half, 7/6, and delta f is 2/3 plus 1, which is 5/3. So all we know from this analysis is that A, we have a fixed point, and B, that fixed point is one where the scaling dimensions are fixed in line with supersymmetry. And one can show, although we've not studied numerically the flow, one can certainly take these equations and numerically simulate them and check that one does flow to the fixed point in great detail.
Mukund, can I ask a question?
Of course, go ahead, Jeff.
At this point, can you say anything about whether this fixed point is unique or not?
Okay, very good. No, we can't, but I'll give you a general argument to say that there actually is a conformal manifold. You see, phi's have dimension 2/3, which means that phi cubed, and there are n such phi's. It means that phi cubed is a marginal operator in this theory. And there are n cubed monomials phi cubed, roughly, because you can pick any combination of the phi's and make monomials. So what this suggests, and this is consistent with the old Lee-Strassler analysis, that there's actually a large conformal manifold whose dimension is of order n cubed. As I'll try to say in a while, the marginal operators are cubic in the fundamental fields, and we don't have access in our analysis so far to these cubic gadgets. We have access to bilinears or double twist operators, but not to triple twist operators. So take various statements I'm making as statements at a generic point in the conformal manifold. I'm not even 100% sure whether you should treat them as statements average over the conformal manifold, but I think in one of those two senses, everything I'm going to say is true. It's certainly true that at every point in the conformal manifold, the dimensions are given by the numbers I've quoted here. But when I come to talking about OPE coefficients and so on, I'm a little less clear on how to think about the conformal manifold statement. Does this help?
Yeah, thank you.
Great. So now we have n dimension 2/3 operators, and we'll continue to call them phi I in the IRCF TFT. And what I want to ask is, what else can we say about the superconformal fixed point? In particular, I want to know about the non-chiral part that's not protected by supersymmetry. That's hard to study with just supersymmetry analysis, spectrum, and OPE data. And the second part I would like to understand is bootstrap consistency. The third thing, which I'd like to understand, which is the thing that I alluded to at the very beginning, namely thermal observables, but I'll postpone that till the end. We don't have results, the full set of results yet. Okay, so let's start by looking at to understand the spectrum and the OPE data. Let's start by looking at the following object. So we start looking at 4-point functions. They should provide us insight into spectrum and OPE. And I'm going to do something slightly non-trivial compared to usual analysis. So bear with me for a second. I want to consider a slightly general 4-point function with some indices. And let me write this expression and then explain what is different from some of the earlier analysis here. It's not conceptually very different, but technically it gives you some more fine-grained insight into the OPE spectrum. So I'm going to consider the following 4-point function, where you see the main thing I've done is I've labeled my fields in the 4-point function by picking the one of n chiral superfields. And I've written this directly in superspace, so this is going to be a supercorrelator, so that I don't have to keep track of individual components. As you can tell, this part of the analysis is much better done directly working with superfields than working with components, because there's just too many components to handle 4-point functions. Now, the usual analysis that's done in the context of SYK, for example, is to consider the following. It should consider what I call the operator average correlator. I.e., you look at the 4-point function I've written above, and then you sum over indices by sorry, there's one thing which is wrong here. This is an L. We can certainly study this. This is an easy gadget to study. And whether we study this or we study the correlator I've written above, when I talk about the correlator, I'm going to average over the coupling. So the G's are averaged according to their distribution. The distinction between the correlator I've written down above and the correlator that's here is that this correlator, which is where I take a sum over the external operator insertions and average over them, only allows me access to a subset of the spectrum. You see, if I have fields phi I, and I have, so this was bars. If I have a phi bar I and I have a phi j, phi L, then the OPE data tells me that this is CILM, something phi bar phi, double twist M. So double twist basically means I'm fusing 2 operators. I'm not fusing more than 2 operators. So I have OPE coefficients indexed by the external operator insertions. And if you think for a second, since all my external operators are of the same conformal dimensions, I have a permutation symmetry that permutes me across the phi n phis. So the full 4-point function can be decomposed in permutation labels as follows. I can decompose it into singlets and adjoints. Just think of phis having a fundamental index and phi bars having an anti-fundamental index under Sn, the permutation groups. So phi bar phi is like fundamental tensor, anti-fundamental that decomposes into singlets and adjoints. The average correlator only picks out, and I'm going to try to be careful here that the operator average correlator only picks out the singlet contribution. It has nothing to say about the adjoint, because the adjoint, if you think about it, doesn't have a trace, and the average basically is like taking the trace in this basis. So if you want the full OPE data, you should, I think, I would say, just examine the full correlator en masse without doing the disorder, without doing the operator average. In all cases, I am doing the disorder average. So if I misspeak, please forgive me. There are too many averages going around here. But this correlator can certainly be computed. And in fact, it can be computed by standard tricks. And it's basically given by summing over ladder diagrams. So there is a sort of pre-propagation part. And then there are two sets of ladders, vertical and horizontal ladders, that you have to keep track of. I'll draw the pictures, and then I won't draw so all the propagators here are now quantum corrected propagators, which I'm not indicating. And there is the vertical ladder.
While you're drawing, can I ask a question again?
Certainly.
So can you compute the 4-point function using something like a shadow formalism, like we did in the paper with Edward and Douglas?
Yes. So I'm coming there.
Oh, okay, good.
Yeah, indeed. So indeed, that's where I'm going. So just for anchoring people, what I'm going to do right now is I'm going to first just compute the correlator, okay, by summing diagrams. Then I'm going to ask, given this correlator, can I decompose it into superconformal blocks so that I know what are the intermediate states propagating in and their transformation properties under the low energy superconformal symmetry. So we'll do those two things in stages, and there are a couple of challenges along the way. So let's see how to do this. So the first statement I'll make is that this correlator, this 4-point function, sorry, keep my indices straight, is of the form, it gets two sets of contributions, and you can check there's one contribution coming from index structure, from the SN index structure, and that can be decomposed into two sets of Canonical delta combinations. And inside this, there's actual dynamical content in terms of the 4-point function of some elementary building blocks, which I'm going to call F0. And this guy takes the following form in a 1/n expansion, where I'm only keeping terms to leading order in the 1/n expansion. Okay. So I'm going to drop terms which are, and I'll tell you what these Ks and Fs are in a second. And this is the same thing with X2 and X3 fleet. This is like a cross-channel gadget. And so everything is accurate to order 1/n. F0 is the free propagator multiplied by itself. So it's basically propagation from x1 to x3 and propagation from x4 to x2. Not the free propagator, the IR fixed point propagator. Now, in distinction from what I wrote before I was just writing a 2-point function for components. Now this is a full super propagator, the propagator in full superspace. And this kernel function k is also a function of xi. With some intermediate positions xa, xb bar. And this is given by, because interactions are cubic, is given by convolving 3 propagators. So we know the G's because they are obtained from the bosonic propagator by replacing bosonic coordinates by super coordinates. And so Gx1 bar x2 is basically the 2-point function of the phi field with the positions replaced by z, where z is some super coordinate, which I can just write out as so good news is, first of all, we know the super propagators. So we know all these expressions, and now we can just start computing them. So we have the explicit 4-point function. And now we can come back to the question that Jeff was asking. This 4-point function is the actual answer. But if we think of what's happening, we have an I index coming in, an I bar index coming in, an L index coming in, and we have K index going out, and the J index going out, and the K bar index going. And we have intermediate states. Which are fusions of phi bar I, phi L. And we'd like to know the dimensions. And there'll be OPE coefficients of the form C I bar L M, C M K bar J. So we want to compute this gadget and this gadget. To do this, we'll need to decompose the 4-point function into superconformal blocks. And here I should highlight a very important paper from about 5 years ago by Bobev, Schock, Mazash, and Paulos, who were the first people to study superconformal bootstrap in 3 dimensions with 2 supercharges. So they worked out a lot of the basic formalism we will need to do this decomposition and extract various of these information. So the kind of information we need is the following. We need the superconformal partial rays, and we need the in the superconformal blocks for 3D n equals 2. So both of this information is available, and there are lots of interesting technical statements about them, which in light of time, I won't go through in detail, but let me tell you a couple of things which are actually quite remarkable. So the first statement which I'll make is that the superconformal blocks, which are functions of conformal dimension and spin, and they can be written, since we are talking about 4-point functions, we can use conformal symmetry to write everything in terms of cross ratios, which I'm calling Z and Z bar here. The superconformal blocks are given in terms of bosonic conformal blocks, with shifted spins and dimensions. And I put indices here. This is for difference of external dimensions. For the left-hand side, I have a n equals 2 superconformal block. This is a bosonic conformal block in 3D. This is useful because, first of all, many properties are known about bosonic blocks. So you don't have to recompute various things for the superconformal blocks. Second, once I say the statement, there's another fun statement that the superconformal partial wave, also a function of the cross ratios, is up to some normalization also given by the bosonic partial waves or the conformal partial waves. So this is two major simplifications in the problem that you can reduce the calculations to stuff that you already know. So this fact was already noted by Bove et al. And we're almost done in terms of the computation, except what took us forever was understanding how to compute this inner product. In the end, it turned out that we could sidestep it. We didn't have to compute it, but in the process, we anyway learned to compute it. So there's a result somewhere in the paper. There's another fun fact, which is related to, what are we trying to do now? We're taking the 4-point function, which is some function of the Z's and Z bars, and decomposing it in some basis of nice functions which are aligned with the infrared superconformal field theory. Since we have an infrared superconformal symmetry, the natural basis functions we want to expand in are the superconformal blocks, whose coefficients will tell us which block appears will tell us what are the dimensions, and the coefficients in front of the blocks will tell us the product of the OPE coefficients. So this is the data we really want, because then we are done with the problem. But to get there, we need to be able to do the decomposition. So we need a complete basis of functions, and that basis is provided by the partial wave decomposition. But what we need is an inner product in a partial wave space so that we can actually take inner products and get the decomposition we want. And the last statement, which is of interest, is that the inner product of the in superspace is actually related to the bosonic inner product in some simple way. So let me quickly tell you that formula, and then we can be off with basically getting all the results we want. So maybe I won't bother writing the formula, but I'll just say here that the inner product in superconformal blocks for superconformal modulus fixed by conformal inner product. And this is what Jeff was alluding to in his question earlier, because this is what you folks had computed in using the shadow formalism in 2D. So with all this in place, we're now in a position to extract the physical results. So let me tell you what the physical results is. The 4-point function, let's do the operator averaged or singlet contribution. For second, can be written. Yes.
Sorry, Mukund, just one more question.
Yeah.
So one of the things that we struggled a lot with was trying to determine what the correct integral measure was for the superconformal for the inner product with in superspace. Is your statement then that even this is fixed by the conformal inner product?
Yes. So what you folks did was to get the inner product, you basically had to undo some standard gauge fixing and re-gauge fix some other way.
Yes.
So you can follow those steps. We in fact did that, and you can get an expression that you need to compute. And you can show that at every stage, various things boil down to doing the same kind of computation for the conformal blocks. And the big deal is that, you see, because the blocks are related and the partial waves are related, the non-trivial part is basically what happens when you do the super coordinate fixing. So if you figure out the Berezinian from the super coordinate fixing, you're roughly speaking done.
Right.
I mean, I'm being slightly cavalier here because Sean spent a lot of time getting this working. But once it works, it's clear that the information was just there.
Right. Okay. Cool.
So let's write down. Let's go back and write down the answer for what we expect for the 4-point function. And I'm going to write a simpler formula. If I put indices, it will be the formula that will be true for the general case, including the non-singlet contribution. And the 4-point function, I will write after decomposing in these blocks as the following. As a sum over spins, an integral over a spectral parameter, or really the integral over the parameter that parameterizes the principal series representation of superconformal algebra. The integral is over conformal dimensions. Have a spectral function which multiplies the superconformal blocks. And all the action is in the spectral function, which tells me what are the, if I look at, so what have I done? Let me say this in words. We have a 4-point function for some set of operators. we know that this transforms in some way under the superconformal symmetry. And the low energy superconformal algebra has a natural basis of functions, the superconformal partial waves and the superconformal associated superconformal blocks. This basis of functions, or the canonical representation for the superconformal algebra, is a principal series representation where the conformal dimensions are not real, but they're sitting on an on a line at fixed real conformal dimension. Imagine the line runs vertically in the complex conformal dimension plane. So physically, we have a picture where we're trying to write the 4-point function in the complex delta plane by integrating over some line, but the physical states are somewhere to its right. So the contour of integration is running up this way. And what we want to do is take this contour and deform it back down and pick up these poles, which are the physical states in the spectrum. And so to extract the physical states and the OPE data, the most compact form is to write down a spectral representation in terms of the canonical basis of superconformal algebra, which is exactly what I've done here after some technical steps which I've elided over, which involve working out the details of what superconformal blocks and superconformal partial waves are doing. But once we have this formula and once we've extracted this rho delta L, we're done. Now we can just start asking, what do we have in the spectrum and what are the OPE coefficients? Let me pause here for a second before I tell you the results to see if there's any questions about the logic of how we got to this point. No? Great. Okay. So with this data, we can now ask what do we have? And we can work out. So I won't write out the expressions. These are all the expressions are some ratios of gamma functions of the external dimensions, delta 5, which is 2/3, and the internal operator dimensions parameterized by delta and spin L. So the double twist spectrum in the theory is something like the following. Spin 0, we have the lowest lying 5-bar-5 state, the non-chiral state. It has dimension roughly 1.7. So all the we have analytical formulas in terms of ratios of gamma functions, but if you want to extract the dimensions, you just have to extract them numerically. So I'm giving you the conformal dimensions and the bootstrap bound that was found by Bogaev et al. By asking what is the bound on the lowest spin double twist field for a given spin. Then we have 5-bar-5 prime, also spin 0. It has delta of 3.4, which is less than, again, the bootstrap bound, which is 5.3. So I write these bounds to show you that this system is well within bootstrap limits. It's not on the edge of any bootstrap constraints. We also have at spin 1 an R current multiplet, which you need to have because we said there's a superconformal symmetry, so we need an R symmetry in an R current multiplet, which includes as in its theta expansion the stress tensor. So this is a necessary characteristic of the superconformal field theory, and indeed we have precisely at delta equals 2, which is since it's a conserved current, the dimensions are protected. a spin 1 primary. You can similarly work out, you can now go to town, you can just work out what happens as a function of, so the spectrum is organized as follows. You can think of the spectrum, the twist of the spectrum is basically given by 2 delta phi plus some oscillator level plus a anomalous dimension, which is a function of spin and conformal dimension. And I've written basically delta directly in the above, but it's much nicer to just look at the anomalous dimension, because this tells you what the deviations are from the free field theory. And one can show that there are asymptotic expansions. So gamma m comma L for large M and large L have constrained asymptotics. Known from analytic bootstrap. And we have all the data, so we can just check that everything works exactly as it should from analytic bootstrap. So it's a nice, if you like, if for nothing else, if this model provides a very good playground for visualizing all the constraints in analytic bootstrap. And so one has, and I won't write out the OPE coefficients. We have expressions for the OPE coefficients, which you can find in the paper, both in the singlet and in the adjoint sector. And one can, some of these are consistent with known bootstrap bounds, although in some cases we have expressions, but corresponding bootstrap bounds aren't known. So it'd be interesting if someone did carry out bootstrap analysis for extended the existing bootstrap analysis to check whether one gets corresponding bounds from as consistent with our analysis. Okay, so I have, can I take a couple more minutes, Jeff?
Certainly.
So there's one more part of the discussion, which I'm going to refer you to the paper. So what I did here was to look at the chiral anti-chiral OP. So I was looking at a 4-point function where we started with looked at the fusion of a phi bar with a phi. This was useful to do because this is the part that's hard to access without using supersymmetry. There's another part of the spectrum where you can look at a correlation function where you have phi bar, which will tell you about phi OPE, which is more constrained by supersymmetry because it's chiral, it's a chiral part of the OP. But that guy is related to this 4-point function by crossing symmetry. So you can use crossing and to start studying, given the non-chiral OP, what the constraints are on the chiral OP and look for consistency. And indeed, we see a lot of consistency in that analysis. But in light of time, I'm not going to spend time explaining the chiral part of the spectrum, which, let me just say that everything is consistent with known bounds and expectations from superconformal algebra. What I do want to spend time on in the next few minutes is a few observations about thermal observables. And I have results, a very limited set of results. So let me first give you the limited set of results and then tell you in closing what exactly we are hoping to do and why I find this problem interesting from this point. So we can compute thermal correlators on hyperbolic 2 space times Euclidean circle by conformal mapping of vacuum correlators. In fact, as Jeff Douglas and Edward discussed in their paper, this is true in all dimensions, and in particular, this is really the remit of Ray-J theory, because the Ray-J correlators are correlators in Rindler space, and Rindler space is conformal to hyperbolic space across time, and I've just compactified time to make it thermal. And what we find is something curious. The hyperbolic, if we take this 4-point function that we have and use it to compute the analog of the out of time ordered correlator in hyperbolic space, we can find a hyperbolic chaos exponent. And we find an exponent which is actually quite low, it's 0.15. For comparison, let me give you the answers in 2D. So this is a result that Jeff and friends had obtained. They had obtained 0.58 in 2D, and in SYK, which is, there's no space, so it's the same thing as the standard SYK computation. It's of course just 1. In 2D, this also happens to be the chaos exponent in Minkowski space, because 1D hyperbolic space is just the line. So there's no distinction here. But in 3D, there is a distinction. Now, this could mean one of two things, and I just want to highlight the two possibilities. It could either mean that the theory we're studying is very far from maximally chaotic, which I sympathize with, and it's partly my intuition that this theory cannot be maximally chaotic, that we're in 3 dimensions, for reasons that I think have to do more with the fact that our disordered couplings are homogeneous over space-time, so so it's not strictly all-to-all type couplings that you see in SYK, because in SYK you have fermions which are all coupled to each other, and there's no spatial information, whereas here you have spatial information, and that's not being disordered. But one needs to be careful interpreting this, because the volume of hyperbolic space also grows exponentially, and it can overwhelm the actual physical dynamical growth of the correlator. So there's a part of this 0.15 is negated, which is by the volume growth of hyperbolic space, and a part that's genuinely the growth of correlations in this disordered infrared CFT. I don't know how to disambiguate those, and I don't think there's a clean way to disambiguate those from looking at this observable. The only clean way to understand what the thermal physics is to compute the correlator in the thermal correlators in Minkowski spacetime. And or R3, we've been trying to do this. We've been stuck with some numerics. It can be done analytically, unlike the previous analysis. Our numerics hasn't quite converged, so I don't have results to show you yet. But I do have 2 questions that I want to share with you before I conclude. One is that there's a sort of basic question which has never really been answered in the context of strongly coupled systems, which is whether what is the analytic structure of 2-point functions? So this question already I would find quite interesting to answer even before getting to 4-point functions. For the following reason, I began the talk by saying that if you look at thermal correlators in weakly coupled systems, you don't see things like viscosity because they're divergent. But there's a more simpler statement, which is that if you look at thermal correlators of systems with quasi-particles, because you have quasi-particles, you have cuts. So thermal correlators in perturbation theory have branch cuts. On the other hand, if you look at holographic examples, thermal correlators don't have branch cuts, they have quasi-normal poles. So the zeroth order question one should ask ourselves as to how strongly coupled the system is to ask, does this infrared CFT have quasi-normal poles? If it does, I would find that very exciting because that's the first example I would know of where you can actually extract quasi-normal poles from field theory. Again, if you look at 2D CFTs, you can find quasi-normal poles, but unfortunately, they're completely given fixed by Virasoro symmetry, so you don't have more information than the vacuum correlator. The other is, of course, the question that the chaos exponent above suggests: how strongly chaotic is this theory? Is it more close to supergravity, or is it some string theory? Does it have a stringy dual? Both of these questions I don't have answers for, but I hope to have answers for you sometime not so long from now. And so with that, let me apologize for going a bit over time and stop. I'm happy to answer more questions.
Thanks very much, Mukund. Any questions? If not, I can continue the trend and keep asking.
Sure.
So I do have one question here. So it's really interesting that this is even less chaotic than our models in 1+1 dimensions. I think I kind of agree with you that you know this really is not maximally symmetric, and I think that maximally chaotic, and I think that I kind of agree also that this really has to do with the spatial information in the system as well. So I tried a little bit at some point to see if what happens if you take this chain of SYK quantum dots that Douglas and Schalang, maybe, I don't know, arranged in this chain. You have and then try and see if because each of the quantum dots is certainly maximally chaotic, and certainly there's a regime in which I can study the coupled dots, and that appears to be maximally chaotic as well. And then is there some consistent continuum limit that one could take and see what happens? Now, I mean, this would just be fermionic. So I try to do this with the coupled, I guess, supersymmetric SYK that Juan and collaborators worked out, and it didn't quite work out. But then I thought then I've been studying a bunch of these systems on quantum networks recently, and there it really does seem that if you take a system, let's say in I don't know 1+1 dimensions or 2+1 dimensions, that the disordered system that contains spatial information kind of suppresses, I want to say, transport properties.
Right.
But essentially, the ability to scramble information is less pronounced once you have to scramble it over some spatially distributed system than in a quantum dot, for example. So I kind of feel like as you go higher in dimensions, your natural systems that live at these disordered fixed points are less and less scrambling in some sense.
Right. I think I agree with you, and I think that I mean, this is a bit more speculative, but one of the discussions that a lot of people have been having is, should we think of quantum gravity in the context of these islands and wormholes as coming from disordered averaging? I think this is in serious tension with that statement, because we know on the one hand that black holes have maximal chaos.
Yeah.
But if you are going to do disordered averaging in field theory, we're not going to get there.
Right. I mean, you'll get there for the very specific ADS2 kind of situation,
right.
But then as soon as you try to go higher than that, yeah. I mean, this kind of leads into what the natural dual of this is, right? And we certainly didn't. We have some speculative comments at the end, but we didn't manage to make any headway on that. I don't think anyone else has in the intervening years either. And I think this is tied into that. I mean, I think that this will be a problem going forward. Yeah, that's a nice interpretation of it as well. I take it you voted no then on the.
I abstained because the question wasn't well defined. But yes, for a well-defined question, I mean, it's like the California recall election. It's a stupid question. So you have to vote. There I have to vote, so I will vote something.
Anyway, thanks so much. This was a great talk. I really enjoyed it.
Great, thanks, Jeff.
Take care.
Take care.